Hi there, this video is about Charles' Law. We're going to talk about math first, which is on the right, and then apply it to a real-life situation, which is kind of on the left. So let's take a look at the math first. You can see in this graph I've got volume on my y and temperature in Kelvin on my x. And if I take a look at it, as I increase the temperature, I can see that my volume has also increased. Temperature and volume are a direct relationship. One goes up, the other goes up. One goes down, the other goes down. What we're going to do is get the gas law for Charles' Law. So taking a look at our equation of the line, let's just look at helium, and then we'll talk about CO2 that's below it. Helium says y equals 0.016x plus 0.026. Now I'm going to disregard that 0.026 part, merely because if the temperature is 0, that should mean theoretically that the volume should be 0. We'll get back to that, theoretically speaking. So we've got y equals 0.016x. I'm going to rearrange this to be y is my v, equals 0.016x, which is my t. I'll divide both sides by t, and I see I get v over t equals 0.016. And just like with Boyle's law, if I take two data points, like I could take this data point right here and call that v1t1, and this data point right here and call that v2t2. So that would be v1 over t1 equals 0.016. Or I could say that v2 over t2 equals 0.016. And if I put the two together, v1 over t1 equals v2 over t2. That would be the Charles' Law, these two things that I circled. So let's apply Charles' Law with a math problem over here. Assume the temperature be increased to a temperature of 155 degrees Celsius. What is the volume that you would need to have? I picked a data point on there. v1 over t1 equals v2 over t2 is our relationship. So my v1, if I looked on the graph, and my t1, let's say I took a temperature of 300 Kelvin. And I'm going to assume using sig figs. I know we can't really tell the sig figs using the graph here, but I'm going to just play sig figs here and say 300 with a point, a decimal point. So I know for sure it's 300, 3 sig figs on my 300. The top volume at 300, it got to be like right here-ish. I call that 4.75. And let's say that's exact and perfect. So 4.75 is the correct number of sig figs. And I want to know what happens at 155 degrees Celsius. Now notice that this is in Kelvin, so we have to convert everything to Kelvin from the start. So I'm going to take 155 Celsius plus 273. Convert from Celsius into Kelvin, you've got to add 273, technically 273.15. And I'm going to find for V2. Now if I do that, I'll use my algebra skills and I'll find first thing that you should do to do sig figs is add these two numbers up. Because the adding rules are trickier, remember. This is 428 if I add the two. Using sig figs with adding, you have to look at the number of places. So in other words, they both go to the ones place. Well, technically 273 goes forever for sig figs. So since my number goes to the one place, my answer for this part goes to the ones place. But a little side trip here. Let's say it's 15 plus 273. Well, 15 plus 273 equals 288. And the sig figs for that would be 288, 3 sig figs. That's because this goes for an infinity number of decimal places. It's a conversion factor, and this one goes to the ones place. So since we know this number in the ones place, we can know this number in the ones place, and we have 3 sig figs. So that's what makes this kind of math problem a little tricky. So always do the converting into Kelvin first. Now that I converted into Kelvin, I can see that I have 3 sig figs on top, and the 300 is 3 sig figs, my 428 is 3 sig figs, so my volume is going to need 3 sig figs, and I get 6.78 milliliters. That's the units we're in right now. Okay, there's the math. Let's take a look at what this all kind of means. Let's say I've got a balloon, and it's at a set volume. And I've got it on this beautiful sunny Jamaica location, and now I'm going to take that balloon, fly it all the way over, and have it directly into the cold snow. My volume is obviously going to change. So let's take a look at that. So suddenly, now that I'm in the cold snow area, my temperature has decreased. If my temperature has decreased, that means the molecules inside the balloon are moving slower, and they're hitting the sides less often. If they're suddenly hitting the sides less often, that means my pressure inside has now decreased. So, my pressure in the balloon is no longer equal to the pressure outside of the balloon. And we know that the world can't work that way, the pressures can't be different. Which means that my volume has to decrease. Thus, when it decreases, I'm going to hit the sides more often, and the pressures can equal out. My volume will decrease, so the pressure inside will increase until the pressure in is equal to the pressure out. And when I did that, I saw that my volume decreased after my temperature decreased. And that was a whole Charles' law. In Charles' law, you change volume and temperature. But what remains the same is your pressure. I know you might be thinking, well, the pressure didn't remain the same. See, you've got things going on. Yes, but the before and the after, the pressures are the same. The before and the after, the pressures are the same. This whole thing works because pressure is trying to be the same. So the pressure is going to be the same, and our N, the number of moles of gas, is going to be the same also. I didn't lose anything out of the balloon. It stayed inside the whole time. So only the temperature and the volume are changing. Pressure and the amount of gases stayed the same. Okay, going back over here to what I said we'd talk about, this point right here. Now I'm assuming that when it's 0 Kelvin, that means the molecules aren't moving at all, so here's our container, and the molecules are just sitting at the bottom. And I'm assuming that the volume technically is 0 when the temperature is 0. Now that's what the gas law says, but theoretically, that's just a theory. In reality, we know that that would be assuming that the gas atoms themselves have no volume, and we know that they do. So it would be a very, very small microscopic volume. So here's where we're taking math, we being the scientists of the world, and we're applying things that are ideal. We're saying, ideally speaking, they wouldn't take up any volume, so thus the temperature and volume would be equal to 0. Well, we know that that doesn't really work well. And so when we talk about ideal versus real gases, we'll hit this too again. Hope that helped.